Hi everyone. This work is called Effect of the Oxidizing Precursor on the ETL Properties of Tin Dioxide. Thin fills deposited by the ALD technique on a hybrid perovskite. Recently, there has been a progress in the fabrication of hybrid perovskite organic-inorganic halide solar cells, abbreviated as PSCS, due to their excellent characteristics. An important part of PSCS is the electron transporter layer. Tin dioxide is a very useful material for various applications, such as transparent electrodes, photovoltaic applications, catalysis, and solar cells due to its attractive electrical properties, high transparency, and conductivity with excellent environmental stability, which are the properties required to be a good electron transporter layer. In this work, the optical, chemical, structural, and morphological properties were investigated to obtain highly conductive tin dioxide thin films by the ALD technique using tetrakis, dimethylamino, tin as tin precursor, and using different oxidizing agents, water, oxygen, and ozone, in thermal and plasma modes, and then deposit it on a hybrid perovskite. The objectives of this project are: study the chemical and structural properties of titanium dioxide obtained by ALD and different oxidizing agents, water, oxygen, and ozone. Analyze the properties as ETL of a tin dioxide layer obtained by ALD using different oxidizing agents, and evaluate the chemical changes of the perovskite after growing an ultra-thin film of tin dioxide by ALD. ALD thin film deposition is based on a separate, self-saturated, successive gas-solid reaction with automatic termination. The ALD process can be divided into 4 steps: exposure of the substrate surface to the pulse of the first gaseous precursor and its chemisorption, inert gas purge to remove excess unreacted precursor, introduction of the second precursor, and a second purge. In the case of ALD in plasma mode, the difference lies in the second half cycle, where reactant species of the gas are generated in the plasma state. When tin dioxide is deposited on glass at 80 degrees Celsius, most of the films obtained are amorphous, with the exception of plasma deposits using water, where a certain degree of crystallinity occurs in the planes 110, 101, and 211. This being an exceptional result. Subsequently, the perovskite was exposed only to the oxidizing agent for a short time. By comparing the relative intensities of the nitrogen signal when using thermal ALD of water and remote plasma of water, it can be seen that when using water as the oxidizing agent in the thermal modality, the signal corresponding to the double carbon amino plus 2 bond, although it is present in the unoxidized perovskite, this signal decreases, reflecting a greater oxidation of the perovskite. Finally, when a complete layer of tin dioxide is deposited using water as an oxidizing agent, both in the thermal and plasma modalities, the absorbance decreases due to the effect of the tin dioxide film on the perovskite. This effect occurs due to absorption of the tin dioxide layer deposited on the surface and interfacial effects. The absorption edge is slightly shifted towards the longer wavelengths in both cases. This shifting can be associated with surface changes of the perovskite in oxidation events. In the SEM micrographs, it is observed that there is a decoration of the perovskite crystals when using thermal ALD of water. When it is used in remote plasma, such decoration is not evident, but the presence of crystals does exist. What has been said above is confirmed with the AFM micrographs, where it is observed with greater contrast how the naturally existing holes in the perovskite are being filled by the new tin dioxide crystals. The conclusions of this work are: crystalline tin dioxide growth was achieved using water plasma at low temperature, showing the dominant effect of the water and plasma on the processes of tin dioxide chemisorption, nucleation, and crystal growth. Although the water plasma favors the chemisorption, nucleation, and crystallization mechanisms at 80 Celsius degrees, it has a degrading effect on the growth of tin dioxide on the perovskite. The emission of light by the plasma and the collisional events of the reactive species with the substrate suggest that conventional ALD processes and those of remote plasma with water at short exposure times are preferred to control degradation. The decrease in absorbance of the perovskite covered with tin dioxide is due to the thickness of the tin dioxide film, as well as to the interface created, which generates optical defects. The growth of faceted perovskite crystals is observed by SEM and AFM, covered with small tin dioxide crystals. Thank you for your attention.